can solve unless you have any questions, concerns, anything you want me to cover or do. No? I think another problem will help. They're never enough. Yeah. Okay, this is a relatively simple one. We may be able to do it both with Euler's laws and Lagrange dynamics, I hope. Lagrange equations, sorry. So this is a circular guide, which is also the ground, and it's inertial, frictionless, and inside, I think this is in your book as well. Inside the track, well, it's not supposed to be this thick. It is a slender, uniform rod that, yeah, it's in contact at points A and B. Again, there is no friction. The length of this is L to L, whatever you want to call it. The radius of the track is capital R. And I'm not going to give you anything else for now, so that we can think about it a little bit. There is gravity. We want to find the equations of motion of this bar, of course. That's the only rigid body I have. No friction. So that's a rigid body. How many equations of motion do you expect? Notice I'm not giving you any variable for now, unlike the other problems. You think it's 1. Why it's 1? We need to pick it, because I haven't given you any variable. It is probably 1. We need to justify why it's 1. So you start from 6. A rigid body in 3D Euclidean space will have 6. We are in a plane. That brings it down to how many? 3. 2 for translation and 1 for rotation. You can only rotate about this axis, and center of mass can move in this plane. So you'll have 3. Now, how am I removing 2 more from here?
It's based on your translation to go on a certain track.
You need to be a little more.
Left is a rotational. Very free.
Well, if this is the center of mass, this is uniform, so this is the center of mass of the bar, I see that moving. It is moving, right? It can move, so.
It's constrained to the track. Like can A and B, can the tips come off the track?
No.
If they're fixed to the track, you can just identify the position by the angle of the center. Well, yeah, the angle from some datum to the center of mass.
Right, so you can pick this angle here as your variable. So I want to say that we start with 3 degrees of freedom, right? Because we know we are in a plane. But then we have 2 constraints, and I agree with that. So you get, in the end, 1 variable that is really needed to describe the configuration of the system. Bless you. So what are these 2 constraints? How would you write them? Because if I have 3 in general for a rigid body in a plane, but then I'm saying that only theta is enough to represent the problem, so I need to find 1 differential equation of motion only, where are these other 2 constraints that remove the degrees of freedom?
This is between A and B.
That is a rigid body. Even if I remove the track, it's yeah.
B cannot go through the circle, so it's attached.
But it can go inside. Can it go inside? No.
And it has the same property.
So I want to say that these 2 constraints are pretty much saying that RA vector is constant, yeah, and RB vector is constant. That's it. Do we see that? So if A and B remain in contact, that means that this angle here is 90 degrees, and we call this distance, I think I have it as B. And so the rotation and the translation of the center of mass are connected to each other, right? They're not independent. This point, if I give you an angle theta, I know where this point is. Make sense? Okay, so we do agree we just need, for example, 1 angle to represent the configuration of the system. And so we pick theta. That's fine. So what do you want me to do? What do you need to do now?
Were you using Lagrange or just classical approach?
I'm going to start with the Euler's laws. So reference frames, I want to say that G is the ground, then I'm going to speed it up, EX as G, right? So let's say that EX is pointing down here. And then, yeah, EY, actually let me do EZ first, because I have a rotation there, right? So EZ, given the sign of theta, I want to say out of the page, right? And then EY is whatever comes out of that. So this is EZ, and this is EY. It's the cross product between EZ and EX. That's one. The origin is at O. Forgot to say that. So these are the axes, and the origin is O. I need a point which is fixed in G. And then the other object is the other reference frame. So call this A. No, I've already used A. A, B, I don't know, C. Am I using C? I don't think so. So this is the name for a reference frame. So C is going to have what origin? Can I use O? Is it fixed? Yeah, this is a rigid body, right? The mass is only here, but we said that a rigid body can be massless in principle, a reference frame. And so if I imagine adding this point to the rigid body, it will remain a fixed distance from the other one. So that's a perfectly fine additional point, or at least it's fixed with respect to the reference frame C. So that's fine. And then I want to say that definitely, well, let's do ER along. Haha. I knew I had to come up with something else here. You know, I really want to call this C and this maybe D. I don't know. Yeah, let's do that. ER along OC. I reuse EZ. Of course, it's big EZ. E theta is the cross product of EZ and ER, and that's it. And so I have, that's pretty simple. Little ER is going down here, E theta is going up here, and this is also little EZ, and this is the angle theta. Okay, done, move on. It's a rigid body, we need to do kinematics. So the first thing you need to do is finding what? Come on, we've done this so many times now.
Position of the center of mass.
Yeah, the position. Well, my end goal would be finding the velocity of C in G and the angular momentum with respect to the center of mass in G. So to do this, I have the position of C, which is, what is that? B little er. Then the velocity of C, actually, I made a mistake there. Sorry about that. That's the acceleration, right? In the first and second laws of Euler, I need this, which is A bar, pretty much. So.
Yeah, because everything is a rigid body.
And this is the.
So if you find the acceleration of C, A, or B, you just find an A bar, right? It's still the same because they're all in the same rigid body.
The acceleration of this point is the same as the acceleration of this point? Are you sure? Is that what the statement was? The acceleration of the center of mass is the same as the acceleration of any point on this rigid body? It is if a rigid body is translating, that is rotating. The acceleration of B, for example, with respect to the ground minus the acceleration of the center of mass with respect to the ground is equal to what? This is equal to alpha of body D with respect to the ground cross with RB minus R bar plus omega dg cross with omega dg cross with R B minus R bar. This is non-zero, this is non-zero, this is non-zero, this is non-zero. I really don't think so. Do not jump to conclusions unless you can be 110% sure that that's right, because it will put you in trouble, okay? If you have a rigid body which is obviously translating, then it's true. All points have same velocities and accelerations, but this is not the case. So Vc in G, which is basically V bar. So let's just do this. Let's remove the C from everywhere. Just call it bar. It's that point C. It's the rate of change of this vector with respect to the ground. So transport theorem tells me that I can do d dt in D of B ER, and this is of course 0, plus what is the angular velocity is theta dot little ez, which is crossed with B ER, which is equal to Ez crossed with ER is E theta. Be E theta, and then I have to do it one more time. So this is in G, I'm sorry, G. Rate of change of this, I'll do the same, first in D and then the cross. So I have theta double dot B E theta. And then I want to go by memory here. Well, this will come from doing omega cross this term here. So it's a theta dot Ez crossing this. So that's your theta dot squared B.
That's a radial one, too.
That's the radial, because Ez cross with E theta is minus ER. Yeah. So that's my acceleration of the center of mass. So I have it here. I'll write it up here so that I can clean up the board. Okay, done. Now H bar. Give me a start.
The inertial tensor.
Inertial tensor. Inertial tensor with respect to the center of mass of D. The angular velocity of the rigid body D with respect to the ground. Okay. Now this bar is uniform. ER, E theta, Ez is what kind of body coordinate system? And this bar has a lot of symmetries, right? E theta is an axis of symmetry. ER is an axis of symmetry. Ez is another axis of symmetry. So what kind of, if I use that as my projection basis, and I better use it because I defined it, why would I have something like that if I don't use it? What kind of inertia tensor do I get? If I have a rigid body and I have obvious symmetries and I select a basis, three vectors, three orthonormal vectors, that correspond to those directions of symmetry, what kind of basis do I have? Principal. Those are principal axes of inertia. So that means that the products of inertia are 0, which means that my tensor can be expressed as, I want to start with R. I circle cross ER plus I theta theta. I'm just going with the order of the vectors. E theta cross circle cross E theta plus I z z E z circle cross E z. That's all I have for my inertia tensor because I don't have the products of inertia, right? And this is multiplying a very simple vector, which is theta dot Ez. So what survives?
IZZ.
That's the only one that survives. All those other tensor products go away. So I have, let me call this, allow me to call this just I. I only have one. I theta dot Ez. That's pretty simple, right? Okay, that's my H bar. I have it here.
I'm guessing this I right here is going to be different from the I for a circle, a uniform circle, right? It's gonna have a different.
These are in your books. So I probably have it in my notes actually spelled out. I don't know, but I just refuse to memorize. It's m. It will be m2l all squared over 12.
Okay.
I don't really care if you have those. You can just leave it as I. I know that this has the dimension of a mass times a distance squared. I mean and it's a constant. Okay. Now, kinematics is done. This is a very simple problem. What does it remind you, looking at it? What kind of motion are we going to get? What do you think? There's no friction, right? Really looks like a pendulum. Probably get the same kind of equation. All right, so what's next?
Free-body diagram.
FBD. Okay, this is my bar, and I have the easiest one I can draw is this one here.
And you have two reactions in each corner.
What can you tell me here?
There's gonna be a reaction for.
Yeah, there's going to be two reactions there. Can you tell me something about them?
Both will be pointing towards the origin.
Why do they point towards the origin?
Just try to keep it on that track.
I can add friction and the reaction in A and B doesn't point to the origin and it still stays on track. And of course, we're assuming that this really doesn't go up here because it can actually fall. But let's just stay below this line if you want.
Let's say B was a infinitesimally small, rigid body too that didn't have a mass and
Yeah.
would collapse.
Well, I can also tell you the same problem, we would be solving the same problem if I told you that this is an additional piece of the rigid body which has no mass and it just keeps it at that distance.
Yeah.
I think that's probably what a book actually gives you. I'm not sure.
That way you can go up without.
But yeah, without worrying about this thing falling, I agree, they point towards the center. Why? When we started talking about surfaces and reaction and we split that into a normal direction and a tangential direction, we called the normal one reaction and the tangential one friction, right? Whatever is in the plane. So there is no friction here. So the only reaction you can get from something like this is normal to the surface, which is the circle. And this is a planar problem. So this could be a cylinder, if you like. And so normal to a circle means something that points at O.
Yes.
That is why. There is a reason. Don't just guess. So if O is here, it's RA is going to be something like this, pointing at O, and RB is going to be pointing at O as well. Okay. So the first law tells me that mg plus RA plus RB equals MA bar G, and I refuse to write it for now. Now I know something about these two forces. They point at O. They're still unknown in terms of magnitude, but I do know the direction. So I want you to tell me how to express these things. So again, the magnitude, I don't know. But you told me it's the direction of the normal. So let's call, for example, the normal in A, NA. Right? So some unit vector that points at O. That you should be able to express it. Same for B. What is that?
It's ER plus.
I don't know. That's not a
goes
unit.
this way and
ER minus is the norm of this is not 1. Well,
I was just talking about vector addition.
I'm telling you, this is a unit vector, so this is not the right answer for sure because the norm is not 1. How about This is just geometry. You need to be able to build your vectors. There's usually not only one way to do it, but the vector NA is what? NA is the vector that goes from A to O, right? Let me write it this way, over its norm. That's one way of doing it. Now, how do you write this?
Oh, you have to write R.
Come on, you have all the pieces that you need. I want to go from here to here and from here to here. It's B ER plus L, well, in that case it's minus,
Yeah.
minus L E theta. Done.
Bring over R, right? After to get NA. Because the norm of AO would be R.
Yeah, B squared, let me see, B squared plus L squared is R. So here is your vector divided by R, I mean. So we can replace this with B ER minus L E theta over, we said R. Sounds like a good idea. Where I don't know this magnitude. Fine. And then you can do the same for RB, right?
B plus.
Yeah. So I'm sorry, but these things you need to figure out yourself. There may be problems where you need to do it. You need to build vectors that are not just given and are not that obvious. But this still, you know, it's an equation or mg. We have to express mg. What is mg? Is mg ex, which is also equal to mg cos theta er minus sine theta e theta. Okay. So if I look at these ingredients I have, the A bar G is already in the little e's basis, so that's nice. The RA and RB, I also have expressed them, except the unknowns here, in the same basis. So everything is consistent in the same basis. So you can write two equations, one along ER and one along E theta, right? Because those are the only ones that appear. I don't see EZ, of course. Everything is in a plane. It will come up from the second law. But I have how many equations here? Two, I just told you. I have two unknowns. I can't get rid of them and get an equation of motion from that. It's not enough.
So you need the third equation.
I need the second law. And my guess is that actually I only need the second law. I could have just not even have done this, but
Actually, the second law, you can actually figure it out without having to worry about the
yeah,
reactions.
right? Which means, what do you want to do? So I don't think I'm going to use this again. So I'll just erase it. Yeah. Okay, so I have h bar, right? And we always start from h bar. And then you're free to pick another point. How many? So what are the options that you have? You have an inertially, you could pick an inertially fixed point. Or you can pick the center of mass. And you can pick whatever. Which one do you vote? I don't like whatever in general. It's not usually very convenient. O is a nice one. It's inertially fixed, so that means the second law actually is in the form that we like a lot, which is d dt in g of h o with respect to g is equal to mo. I don't have the extra terms, right? Because it's an inertially fixed point. These two reactions point at O, so they go away. So the only thing that I am left with is mg is the moment from mg. So we need to figure out mo, and let's do this first. Let's move h bar to O. That's the annoying part, I know. It's not too bad. So ho in g is equal to h bar in g plus Ro minus R bar crossed with the mass of the system. Oh yeah, by the way, this is mass m. Completely forgot to tell you the mass of this is m.
And then it's VO minus bar.
It's V of O in G minus V of the center of mass, velocity of the center of mass in G. Now this is 0.
That's nice.
Yeah. And also the position of the center of mass. Since both reference frames have the origin at O, that is actually 0. So I have only I theta dot Ez minus R bar is B ER, right? Which is crossing M. Let me see here. Oh, yeah, I erased the velocity.
So it was theta dot B E theta.
Say it again, sorry.
Theta dot B E theta.
Theta dot B. Oh, yeah, it was easy. Yeah. With a plus? I think so. Yeah, with a plus. Yeah, with a plus. Okay, yeah. So the minus with the minus goes away. So this will be I theta dot Ez. What am I doing here? ER cross with the theta.
It's easy. ER.
Yep, it's another Ez. Of course, it needs to be with a plus. So plus, minus, plus, all pluses. MB squared theta dot Ez. So you can just say I plus MB squared theta dot Ez. That is really nice. We need to take the time derivative of this. So ddt in G of that vector is simply I plus M B squared theta double dot Ez, but you need to make sure that this is possible. Ez is fixed in G. In principle, the vectors that belong to the reference frame D are not fixed in G. ER and E theta are not. Only Ez is. So that's why you can do that. And you don't need the transport theorem. Fine. What is MO? It's
BER
something cross MG.
So it's going to be BER cross MG.
Can you tell me how we expressed this before? I think it was cosine of theta.
ER minus theta.
I'm almost writing with my fingers here. Okay, sine of theta, E theta. Am I missing something?
You're going to get a negative. Negative.
That goes, this is 0, ER cross with ER. Then I have an ER cross with E theta, which is an EZ, of course, with the plus, but then there is a minus, minus B M G sine of theta EZ, done. That's your equation of motion. Make sense?
Yeah.
Okay. Told you it wasn't a difficult problem, but it's a good refresher of what you do with the second law in particular. You need to
So
pick.
you didn't need the first law then?
I didn't need it in this case, and that's pretty much what happened with the simple pendulum. You can do it with angular momentum only, and you're done. Do you want to do it with Lagrange's equations? I will say yes. Let me write the equation we got here just for fun. I plus MB squared theta double dot. Well, I just projected MBG. Okay. So the first thing that needs to come to mind is what are the things I can forget about if I use Lagrange's equations?
The reactions.
Can I forget them?
Yeah,
Because they are constraint forces. So who cares about them? No one. I need to compute the kinetic energy, which is 1 over 2 mass, velocity of the center of mass, dotted with itself, plus 1 over 2 h bar g dotted with omega dg. And this is going to be 1 over 2 mass b squared theta dot squared, because I think that was the velocity along e theta with the plus. Yep, plus I have h bar right here. If I dot it with omega, I get a theta dot squared. Right? Yep. So I get a 1 over 2 I theta dot squared. That's it. Yeah, it's pretty sweet. This is a simple problem. And then we'll take the derivatives. And I need q theta. What is q theta?
It's going to be energy partial
There's only one force we care about, right? mg dotted with the partial of the position of the center of mass. That's where I'm applying that force, r bar with respect to theta. So let's figure this out. Okay, this was r bar was b er. We've done this before. This means b cos theta ex plus sine theta ey. And so if I take the partial of r bar with respect to theta, I take derivatives of... No. Is that wrong?
I think, yeah, no, it's fine.
That should be...
This is the EX one that was confusing, but no, it's fine. We find theta, it's fine.
Yeah, yep. Okay. So, yeah, we just take the partial of these, wherever you see theta, that's your variable. So you get a b minus sine of theta ex plus cosine of theta ey.
That's E theta, right? Yeah, that is E theta.
So when you're doing the partials, don't worry about throwing that theta dot in there.
No, because you're just taking the
This is a
partial
partial.
theta.
This is partial with respect to theta. When you...
If you were doing the dt,
Yeah.
then you would have to carry it out because theta would be a function of time.
Yeah. So when you do the partial with this symbol, it means that you may have a million variables in your function. You only care about treating this one as the only one that is changing. So you take partials only of the functions where you see theta, nothing else. Okay, and then I have to dot this with mg, and mg was mg cos theta. What am I doing? Oh, that's it. That's already in EX. I don't need to do that. I don't know why I'm doing this. mg EX. So this is actually q theta, again, is mg EX, which is dotted with b cosine of theta. I don't know what I'm writing here. Minus sine of theta EX plus cosine of theta EY.
Oh, that's awesome.
Yeah, this is nice.
You already got
This
the-
dot goes away. I have a minus mgb.
Sine theta.
Yeah. That's it. Right there.
Yep.
So that will be your right-hand side of the equation. And then we'll take...
Partial t, partial theta is 0, so
Yep.
that's the thing.
Is it?
Yeah,
It
there's
is.
no theta on that.
Okay, so my left-hand side of... So q theta is this.
And partial
This was my q theta.
theta dot is mb squared.
Just
theta
as-
dot
As a refresher, your ddt partial of t with respect to theta dot minus partial of t with respect to theta equals to q theta will be your equation of motion. So ddt, I'm sorry, partial of t with respect to theta. I don't see any theta in this formula here, so this is 0. And then partial of t with respect to theta dot
Take
is,
out the 1/2 and take out the,
yep,
the square.
mb squared theta dot plus I theta dot. Sounds familiar.
And you just have to dt that.
I plus mb squared theta dot. Take the rate of change with respect to time. You only get theta double dot. And that's your equation of motion again. Pretty simple.
4 minutes.
Yeah. So I do strongly advise that with the time you have left until Tuesday night, you keep solving problems both ways. And think through the steps. Don't just go by memory about what you have done in the previous one, because the chances that you make a mistake are pretty high. At least that's what happens to me if I try to just memorize stuff and reuse it. Just use principles. Any questions? Anything else you want me to cover? What I'll do Monday is really outside of, well, it still has to do with rigid bodies, but I just want to show you one more application on how the stability of the spin motion of a spacecraft is analyzed using the second law of Euler. So it's just to conclude the class with some application that interests me in particular, but since it has to do with spacecraft. But I don't know if you guys have anything else that you want to see. No questions, no concerns? So we have some more time. I can probably start what I'll do on Monday. At least give you the why we care. So imagine you're flying your satellite around the Earth. It doesn't really have to be around the Earth, around some planet, or even in deep space. It doesn't really matter. This is a planet. This is some orbit. And say that you have some type of sensor, maybe it's a telescope, maybe it's a Hubble. Maybe it's Hubble or something similar. You have something that needs to point in a fixed direction in space. So you may want your satellite with some type of sensor to look always in a certain direction, which is maybe fixed in an inertial reference frame. And sometimes we use the Earth, even for satellites flight. We use the Earth as an inertial reference frame, even though it's not. Not exactly the Earth. What is usually done, the center of the Earth is used as the origin of a coordinate system which is assumed to be fixed in an inertial frame. Then the axes that originate from that point at some given stars that don't seem to change position.
They change very slowly, right?
Yeah, in a pretty long time. And so we call this reference frame, which is not spinning with the planet. The planet can spin, this doesn't. These EX and EY are not going to spin with the planet. Just the center is the center of the Earth. We call this ECI, Earth-centered inertial frame. And so basically say that this satellite wants to point for some reason in EY, in the EY direction, I don't know, some fixed direction in space. One way to make this configuration stable, so you basically want, as the satellite flies on its orbit, you want it to remain always in this orientation. And the shape doesn't really need to be that shape. One way to make this motion stable, so try to resist any perturbations, is to give the satellite a spin about this axis. So once it's outside of whatever has launched the satellite into orbit, once it's injected into orbit, there are some maneuvers that basically align it to the direction that is the desired one, and some angular momentum is created so that there is spin, there is an angular velocity about this axis. And so what I want to do is next time is start studying the stability of this motion, and we'll see how you can't just pick any of the body axes of the satellite to have a stable motion. Only two of them are actually stable: the axis of minimum inertia and the axis of maximum inertia. If you have an object that has a shape so that you have three principal axes with three different moments of inertia, and they're all different, say that you have a matrix of inertia which is, I don't know, 10, 5, 2. You have found your principal axis of inertia and you've computed this matrix of inertia. These are kilograms meter squared. So, and these will correspond to some body axis EX. This will correspond to some body axis EY. This will correspond to some body axis EZ. If you spin your satellite about this axis, in principle, for what will derive next time, it's stable. About this axis also is stable. If you do it here, it will not stay there. The object will start a spin about that axis, but it will try to go away. It will end up spinning about one of the other two axes. And so what you want is build your satellite so that it can spin about the correct axis, of course. And then, so we'll derive from Euler's second law the equations that show us. Do we have until 35 or 30? Pretty good. So, what I was going to say. Yeah, you have to spin it about the appropriate axis. Otherwise, yeah, you will see a weird motion. It will go away. Why do I care about? Say that in this case, I'm spinning about the EX body axis. So my angular velocity of the spacecraft in this case, with respect to the ground or the inertia reference frame, the ECI, is given as initially some omega bar, some constant on x EX, because I know that that's an axis which is going to make it stable. So why do I care about maintaining a condition like this? If you think about what's going on, these components are the projections of the angular velocity vector in your body axis, right? If you go back to the lecture where we covered Euler angles, and you look at those equations, if you only have one component, so your omega vector is, in this case, some omega bar x 0, 0. If you only have one, you will see that the angles evolve in time in such a way that two of the other angles remain as 0 or fixed, and one is just increasing or decreasing, or there's only one angle changing, which is the spin axis angle. So in other words, the Euler angles of this object, if this is the axis about which I'm spinning, the only angle that is changing is the spin angle. The other two are not changing. So this is actually remaining inertially fixed in terms of pointing that way. Does it make sense?
What do you mean the Euler? It's not change.
Well, do you remember the definition of Euler angles? You have a reference, the ECI, coordinate system, EX, EY, EZ, right? And if you pick a 3, 2, 1 rotation, for example, to go from this axis to your body axis, you do a first rotation about this one of a certain angle. I don't remember what I called it. Let's call it theta 1. This was the rotation 3. Then you do a rotation about the second intermediate axis, theta 2. And you get these axes down here, and this other axis goes up here. And then your final one is about this last axis, theta 3. So this also is going to change, and this is going to change, right? So imagine that I basically don't have the theta 2 and theta 3. You only are spinning about the z-axis. Does it make sense? I see that's one of the formulas I don't memorize. But if you go back to the expressions that give you theta 1 dot, theta 2 dot, theta 3 dot, there was a matrix in between, right? And then here you have your omegas, omega 1, omega 2, omega 3. So if you kill two of these, you only have one left. You will have one other angle that is changing, the other two don't change. And that's exactly what I want. I only want, because say that this is my spacecraft spinning about the z-axis in this case. There is a sensor that needs to look up at the ceiling. It will remain looking up at the ceiling. The other two angles are not going to change. If they change, it will do this. It will go away from that pointing condition.
But wouldn't that be if the matrix that's multiplied there is linearized? Because if it's not, if it's non-linear, diagonal, if it's non-diagonal, then theta 2 and theta 3 could be, functions of omega 1. I'm saying theta 2 dot and theta 3.
Well, you have to. Well, of course, I'm assuming that you're starting from initial conditions where the other two are also 0. So I don't have it in mind. But if you have all the angles starting at 0 here, and you start integrating this equation with two of these components 0, they will basically, the two angles will remain at 0. If you think about it, it's a very simple problem. It makes sense. Grab an object and just make it spin about one axis.
You're translating at the same time. That's what's confusing.
Well, it doesn't matter that it's translating at the same time. Again, we'll see these from Euler's second law more in details, but it doesn't really matter because the second law is actually given with respect, you can write it with respect to the center of mass, d dt g of h bar g equals m bar. And when you are in orbit, and if you write it with respect to the center of mass, you can approximate that the gravitational force is at the center of mass. So that is not going to change your h bar. This is 0. So you can basically forget about the motion on the orbit. You can only focus on the second law by itself. We'll see it. I'll write them down. But the point of creating spin about one axis is try to make the system resistant to changes so that it stays spinning about one axis. And it's pointing that way. Now, we'll find out that from Euler's second law that it looks like the second and, the minimum inertia case and maximum inertia case are the stable ones, but, and these are the links that I sent you. In 1958, the Explorer 1 was launched, and it was designed to spin about it, like in that case. It looks like a pencil. It's a very long, a cylinder. It's a very long satellite. And it was designed to spin about the axis of minimum inertia, like in this sketch. This would be the axis of minimum inertia, right? This axis has, if this is a cylinder, this has higher inertia, right? Moment of inertia. So it was designed to do that, which according to Euler's second law is stable. After not too long, he actually went away from that configuration. It did some strange motion, and he ended up spinning about this axis. Because there are other things that were not taken into account. The fact that no system is perfectly rigid. So there's still very minimal dissipations of energy due to flexible modes, and all sorts of other things going on. So that basically after 200 years after Euler, they had to go back and say, okay, there's something else that we haven't modeled here. And they came up with the reason why this is actually not stable. So we'll derive why mathematically from Euler's laws. If you spin something, and I have to define what stability means, so I will do that as well quickly on Monday. But we'll derive that in principle these two axes, if you put something spinning about those two body axes, it will tend to remain in the vicinity of that axis. So if I go there and I hit the system that is spinning, yeah, it will go away from that axis, but it will not diverge. It will try to stay in the vicinity of that axis, which is what you want when you're pointing something. And so that's what rigid body mechanics shows us, but then it is not true. Experimentally, not too long ago, if you think about it, in the 50s, they found out that one axis is not stable. If you put a satellite spinning about the minimum axis inertia, it will go away from that condition, and it will do something else. So it wasn't pointing where it was supposed to point. They had to adjust to that new condition. So, next time I'll bring the formulas for this, and we'll take a look about Euler angles a little more in details, so that we are convinced that if you put something spinning about one axis, there is a very simple. You're basically looking at a problem in the plane, like the one we've just done. This object here, for which we solved the problem, has an angular velocity that is only about the z-axis, and the only angle that is changing is theta. That's pretty much what happens when you spin about one axis. That's it. But we'll see it. Okay? I'll see you Monday.